All right, welcome scholars. Congratulations. This is it, right? This is the last of the new material, right? So let's get into this. Okay. But it is a long section. It's like almost 60 slides, so, we'll see. So, for our last topic, we're going to be moving into chapter 11 on systems of equations and inequalities. And we're going to be working on section 11.1, system of linear equations in two variables. A few learning objectives here. Hang on. Okay, so a few learning objectives here. I like to pretend I took that photo. Looks like I'm just going for a hike or something. In this section, you will solve systems of equations by graphing, solve systems of equations by substitution, solve systems of equations by addition, identify inconsistent systems of equations containing two variables, and express the solution of a system of dependent equations containing two variables. Okay. So there are three types of systems of linear equations in two variables. We have an independent system, has exactly one solution pair. That's where the lines intersect. We have an inconsistent solution that has no solutions. That occurs when we have lines that are parallel and they never intersect. And then we have a dependent system, has infinitely many solutions. And this is where one line coincides with the other or lays on top of the other, or in other words, is a multiple of the other, right? So we have infinitely many solutions there. So given a system of linear equations and an ordered pair, how to determine whether the ordered pair is a solution? Substitute the ordered pair into each equation, and it should make both equations true. So determine whether this ordered pair is a solution to the given system, okay? So when x is 5 and y is 1, does it make it true? Let me see, 5 plus 3 times 1. The question is, does that equal 8? Yeah, 8 equals 8. So it makes that one true. Let's see. 2 times 5 minus 9. The question is, does that equal 1? Well, 10 minus 9, does that equal 1? 1 equals 1. Yeah, right? So is the ordered pair a solution to the system? Yes, because when we replace x with 5 and y with 1, it makes both equations true. We're already a sixth of the way there. Substitute, that's the solution, yeah. So we got that correct. And then if we were to look at the graphs, we would see that's where these two graphs would cross or intersect, right? So in a graphical sense, the solution to the system is where the graphs cross or intersect each other. I guess this is fine the way I have it for now. Solve the system by graphing, okay? Let me see. So let me introduce some graph paper here. And I'm gonna take some notes real quick before we go heavy into it. So for me, I feel like now there's a couple of ways we can go about graphing these. Notice that the highest power is a 1, so these should both be lines. We could like plot the intercepts, like the x-intercept and the y-intercept, or we could solve for y. I'm gonna do the first equation in blue. And I'll do the second equation. Well, that's irking me. Thank you. Guess we can go orange. Okay. I feel like I think I just prefer to do the intercepts. I was going to solve for my y and then use that, but let's start off with the y-intercept. So if we set x to 0, so So when x is 0, the corresponding y is negative 8. And for the x-intercept, if we let y be 0, then it's like x is negative 4. So that's the x and y intercept. Let me see. For the first one, and then for the second one, when x is 0, y is 1. And then when y is 0, x is negative 1. Right? So I feel like let's just kind of go with this. Okay. So our x's, we went as low as negative 4. Our y values. Okay, so it looks like we're kind of focused on kind of quadrant 3. So like if this is our origin, we just need to get down to maybe like negative 5. So let me see, we can go like 1, 2. Let's see, 1, 2, 3, 4, 5. Okay. So this is our positive x. Our y values, we went as low as negative 8. Let me see. Let's see. 2, 4, 6, 8. So that should be good about like that. So our positive y is in this direction. Here's the origin. I think we went 1, 2, 1, 2, 3, 4, 5. These are negative. I think we went by 2's here. 2, 4, 6, 8, and these are negative. Okay, the first one, we've got a 0, negative 8, which is here. And then negative 4, 0 is here. Okay. Okay, so that looks pretty good for the blue graph. And then orange, we have 0, 1, which is here. And then negative 1, 0 is here. Okay. So then now we drew it to scale because we were finding an answer. We needed to kind of be drawn to scale. So it looks like they intersect at the point negative 3, negative 2. Okay. So our claim is that the solution to the system is going to be the ordered pair negative 3, negative 2. And we would check by plugging into the original to make sure that this ordered pair makes both equations true. Okay, and what I'm going to do, okay, let's just do a check real quick. So then 2 times negative 3 plus negative 2, the question is, does that equal negative 8? That's going to be a negative 6 minus 2. Does that equal negative 8? Negative 8 equals negative 8. So that checks out. And again, this is our check. And then negative 3 minus a negative 2. The question is, does that equal negative 1? So then that's really negative 3 plus 2. Negative 1 equals negative 1. So that checks out as well. Okay. So we've verified that negative 3, negative 2 is the solution graphically, and then we checked it to make sure that it makes both equations true, and it indeed did. So then we can be confident that that's the solution to the system. Okay. It makes both equations true. Okay. Can graphing be used if the system is inconsistent or dependent? Well, yeah. Okay. So if the system is inconsistent, then that means our lines are going to be parallel, and there's not going to be a solution. If the system is dependent, meaning one function is a multiple of the other, we're going to have infinitely many solutions. So, I mean, yeah, we can use the graph to get a sense of what's going on with our system. I would say yes. Now, not necessarily to solve it, but it'll give us a sense of what's at play, right? So in both cases, we can still graph the system to determine the type of system and solution. If the two lines are parallel, the system has no solution and is inconsistent. If the two lines are identical, the system has infinitely many solutions and is a dependent system, right? Okay. So now we're going to look at solving a system of equations by substitution. Given a system of two equations and two variables, we want to see how to solve using the substitution method. I'm going to let you read through that on your own, and I'm just going to explain it as I go. I feel like that's going to be more clear than what they're doing. Maybe not, but I'm going to do it that way. Solve the system by substitution. So if we're going to do substitution, we want to solve one equation for one variable. For instance, in that first equation, it looks like solving for y would be the most simple. So we'll get like y equals x minus 5. Then we take that, plug it into the second equation. At that point, we should have one equation and one unknown, and so we should be able to solve. Every time we have an unknown, we need an equation, right? So if we solve for y from the first equation, again, we get y equals, if we add x to both sides, we get x minus 5. We're going to take this and plug it into the second equation. So we're going to have 2x minus 5 times y equals 1. But what is our y? Our y is our x minus 5. Okay, now at this point, we have one equation and one unknown, so we should be able to solve. We're going to distribute this negative 5. Okay. Minus 5x plus 25 equals 1. Okay. So 2 minus 5 is a negative 3. I'm going to move the negative 3 to the right. I'm going to add 3 to both sides, or 3x, and subtract 1. We'll get 3x equals 24. So what is that? X equals 8. Guess I'll keep working here. Okay, so if x is 8, then y is going to be 8 minus 5. So y equals 3. Okay, I'm just going to keep working over here. So our claim is that the ordered pair 8, 3 is a solution to the system. Okay, and let's just do a quick check. So is it the case that negative 8 plus 3 equals negative 5? Negative 5 equals negative 5. So that one checks out. And then 2 times 8 minus 5 times 3, does that equal 1? That's a 16 minus 15. Does that equal 1? 1 equals 1, right? So then we can be confident that the solution to the system is the order pair 8, 3. So this was a demonstration of the substitution method. Again, with the substitution method, We solve one equation from one. We solve for one variable from one of the equations. We take that, plug it into the other equation, and then at that point we have one equation, one unknown. We can solve. We solve, and then we back substitute to find both x and y. Okay. Okay. Can the substitution method be used to solve any linear system in two variables? I would say yes. I don't see why not. What about vertical? Like maybe not if we're doing vertical and horizontal. Let me see. Yes, but the method works best if one of the equations contains a coefficient of 1 or -1, so we don't have to deal with fractions. Okay, that's fine. Okay, so we saw the substitution method. Now we're going to look at this technique called the addition method. And again, I'm going to let you read through that on your own, and I'm just going to explain it as I go. Solve the system by addition. So when we do the addition method, the first goal is we want one of the variables to have the same coefficient with opposite signs. So it's already done for us here. So then we can just add the two equations together. All right. Once you get, and the way you get one of the variables to have the same coefficient with opposite signs, you can multiply any row by any non-zero number. Right. So I'm sure we'll see an example where we'll have to do some manipulations to get this effect. But in this example, we got lucky that they already have the same coefficient with opposite signs. So then once we have that, we just add our equations together. Okay. So if we add these guys together, 1 plus -1 is 0. 2 plus 1 is going to give us a 3y equals 2. Ah, boo. Okay. So y, and divide both sides by 3, y equals 2/3. So then if y is 2/3, we get this -x plus 2/3 equals 3. -x, let me see. 9/3 minus 2/3 is a 7/3. I'll just kind of work over here. So then we get that x equals a -7/3. Okay, so our claim is that the solution to the system is going to be -7/3, 2/3. I'm just going to use my prepared notes. We should check it. Let me see. I'll just check it. I mean, we can do it. I'm just being lazy. Let's check. All right. So then -7/3 plus 2 times 2/3, does that equal -1? So that's a -7 plus 4. That's going to be a -3/3. Does that equal -1? Yeah. All right. -1 equals -1. Running short on space. -7/3 plus 2/3. Does that equal 3? 7 plus 2 is 9 divided by 3. It checks out, right? I'm just running short of space. 9, because 7 plus double negative is positive. 7 plus 2 is 9, because they already got a common denominator. 9 divided by 3 is indeed 3, right? I just did it that way because I ran out of space. Yeah, so what we have is correct. Okay, we're about halfway. Using the addition method. Okay, so now here's one where the coefficients don't have the same numbers. So we can use multiplication. We can multiply any row by any non-zero number and preserve our outcome. It won't affect our outcome. So again, the goal is for one of the variables to have the same coefficient with the opposite signs. So what I'm going to do is multiply the second equation by -3. All right? So that times negative 3, each of these by negative 3, okay? So then if we do this, the first equation stays as is. It stays as 3x plus 5y equals a negative 11. And if we distribute a negative 3, we'll get negative 3x plus 6y equals negative 33. Now we're ready to add the two equations together. A number plus its opposite, they add to 0. 6 and 5 is 11y. That looks like what? Negative 44. Divide both sides by 11, y equals negative 4. Okay. So I'm going to plug this into the second equation. You can plug it into either one, but to me, it looks like the second equation might be easier to work with. So if we keep working over here, x minus 2 times our y equals 11. So then that's really what? 8. So x plus 8 equals 11. Subtract 8, x equals 3. So our claim is that the solution to the system is the ordered pair 3, negative 4. And again, we should check to make sure that this works. Let's just do a check real quick. Let's not be lazy. Like, lazy has such a negative connotation, but it's only natural, right? Energy follows a path of least resistance. If we are energetic beings, right, if we're energy at our core, right, essentially spiritual beings having a human experience, or, you know, some people call it spirit, some people call it energy. But energy is going to naturally follow the path of least resistance, right? And so in English vernacular, whatever, it has a connotation of lazy, which has a negative connotation. But I think the thing that makes us divine is that we can override that natural thing, and we can like do things that are unnatural, right? To elicit a different effect or response, right? So to me, that's what makes us divine. So in one context, you might call it lazy, but in another context, you might call it efficient. I feel like efficiency is the positive connotation of lazy, where you're doing the least amount possible but still meeting your objective, right? So it's all perspective and context, in my opinion, right? But I do want to showcase this and show you that it works, so that's why I'm writing it out. Okay. So let's see. So for the first one, we got 3 times 3 plus 5 times what? Negative 4. The question is, does that equal negative 11? That's going to be what? 9 minus 20. Does that equal negative 11? 10 and 1, negative 11, right? Negative 11 equals negative 11, okay? And then with the second one, we have 3 minus 2 times negative 4. Does that equal positive 11? 3 plus 8, does that equal 11? 11 equals 11. All right. So this ordered pair makes both equations true, so then we can say that it's the solution to the system. Okay. Solve the system of equations in two variables by addition. Okay. So let me see. We're going to have to change. Now, I think in the first one, we were able to just add the two together and it worked. The second one, we had to manipulate one to get it to work. And this one, it looks like we're going to have to manipulate both equations to get it to work. So I'm just going to choose. Actually, I'm going to choose to eliminate my y's. I feel like I'm just going to choose to eliminate my y's, right? Let me get a copy of the original. So we have this 2x plus 3y equals a negative 16. And we have this 5x minus 10y equals 30. Okay, I'm just choosing to eliminate my y's. You can choose whichever one you want to eliminate. Now, if I want to eliminate the y's, I need them to have the same coefficient with opposite signs. So I'm going to get both of those y's to 30 with opposite signs. So the first one, I need to multiply by, what, 10? So I'm going to say times 10, times 10, and times 10. With the second one, I need to multiply by 3. So I'm going to say times 3, times 3, and times 3. Okay. So the first equation is going to turn into, what is that, a 20x plus 30y equals a negative 160. And if we distribute a 3 across the second one, we're going to get 15x minus 30y equals 90. Man, there's some sirens going off in the distance. I don't know if it's an ambulance or police chase, or that sounds pretty wild out there though. Okay, so now we can add these two equations together. A number plus its opposite adds to 0, so the y is gone. On the left, we get 35x. 10 and 6 is 70, so a negative 70. Divide both sides by 35. What is that, a negative 2? Okay, I am going to plug this. I'm just plugging into the second equation because I feel like it might be easier. I'm just choosing one. So if x is negative 2, then we're going to have 5 times negative 2 minus 10y equals 30. So that's going to be a negative 10. Negative 10 minus 10y equals 30. So add 10 to both sides. Negative 10y equals 40. Divide by negative 10, y equals a negative 4. So our claim is that the solution to the system is the ordered pair negative 2 comma negative 4. And again, we should check to make sure it works in both. So 2 times negative 2 plus 3 times negative 4 equals a negative 16. Negative 4 minus 12. Negative 16. Negative 16 equals negative 16, okay? 5 times negative 2 minus 10 times negative 4, does that equal 30? Negative 10 plus 40, does that equal 30? 30 equals 30. Okay. So we can be confident that negative 2 comma negative 4 is the solution to the system. Okay, we got what, like 20 slides remaining. Let's keep going. Solve the system in 2 variables. Okay, let me start by getting a copy of the original. We got this x over 3 plus y over 6 equals 3. We got x over 2 minus y over 4 equals 1. Now, I'm going to use this technique that I like to use. We can actually get rid of all of these fractions, right? This technique, let me see. If we start with the largest denominator is 6, right? And we just go denominator by denominator. Is 6 a multiple of 3? Yeah. Is 6 a multiple of itself? Yes. Is 6 a multiple of 2? Yes. Is 6 a multiple of 4? No. All right. So then we're going to say 6 times 2, which is 12. Is 12 a multiple of 3? Yes. Is 12 a multiple of 6? Yes, yes. And is 12 a multiple of 4? Yes. So the least common denominator is going to be 12. So we can multiply every term by everything by the least common denominator. So we're going to say this times 12 times 12 times 12 times 12 times 12 and times 12. And what this will do, this will get rid of those fractions and preserve our final result. It'll preserve the solution. So 12 divided by 3, that's going to change it to 4x. 12 divided by 6 is a 2, so that's going to change into 2y, and that's going to be a 36. That's going to be a 6x minus 3y equals 12, okay? So now we want to pick a variable to try to eliminate. I think I'm going to try to eliminate the y, and the least common multiple between 2 and 3 is going to be 6, right? So what I'm going to do, I'm going to say this times 3, each of these times 3. If I'm trying to get this to 6, I'm going to say each of these times 2. Okay, I'll work over here. So 4 times 3 is what, 12? 12x plus 6y. 90 plus 18 is 108. Okay. The second row, we get 12x minus 6y equals 24. So now notice our y's have the same coefficient with the opposite signs. So now when we add our equations together, these guys are going to cancel. We're going to get 24x equals 132. Is that right? So then x equals, hey Google, what's 132 divided by 24?
132
Is it
divided
8?
by 24 is 5.5.
5.5. Okay, so we got 5.5. We should probably do fractions since we started in fractions. So 5.5, 11 over 5. 11 over 5, right? No, 11 over 2. Yeah, there it is. Okay, I guess they're both about the same level of difficulty, so I'm going to plug it into the second equation. If we replace x with 11 over 2, then we're going to get 11 over 4 minus y over 4 equals 1. Okay. So then we get y over 4 equals 11 over 4 minus 1. Okay, 11 minus 4 is 7. So we get y over 4 equals 7 over 4. Is that right? I feel like I made a mistake somewhere. So then we're getting y equals 7. Let's check these. We definitely need to check these. This looks weird. So our claim is that the solution 11 over 2 comma 7. I feel inclined to just use the calculator. 11 over 4 minus 7 over 4. That's indeed 1. 11 over 6 plus 7 over 6 is 18 over 6, which is 3, right? So it actually makes both of them true. So I think this is it. 11 over 2 and 7. 11 over 2 and 7 is correct. Okay. Okay. So with this one, notice that they already solve for x, so we might do the substitution method here. So let's try substitution since they've already isolated the x in one of the equation. So let's take the x and plug it into the second equation, and we'll get 9 minus 2y plus 2y equals 13. Number plus is opposite. This adds to 0. And if we subtract 9, what is that? 4? 0 is not equal to 4, right? So, you know, so 0, because 0 is not equal to 4, this is a contradiction. So there's no solution. We'll just say no solution. The lines are going to be parallel. In other words, these are lines that have the same slope with different y-intercepts. Okay? So we'll just say no solution. Mm-hmm. So again, showing that the lines are parallel with different y-intercepts is another way we can do that. Oh, it's 11:11. Okay. We're almost done. And this is a pictorial representation of what's going on there. Okay. So same deal here. Let's see. We can use the addition method. So let's get the x's to have the same coefficient with the opposite signs. I'm going to multiply that first equation by -3. Okay. So then if we do this, we'll get -3x minus 9y equals -6. And the second equation stays as is. If we add these together, we get what? 0 equals 0. This is true. So what this means is that one equation is a multiple of the other, and we have infinitely many solutions, right? So then they're going to take on the form no matter what x you choose. Now, if we solve for y in like the first equation, subtract x and divide. Looks like y is going to take on the form of -x plus 2 over 3, right? So no matter what x we choose, y takes on that form. You know, you can choose x, you can find the corresponding y by doing this, and then check that the order pair makes both equations true. All right, let me see. Siri, give me a random number between 1 and 10.
A random number between 1 and 10 is 6.
Okay, so for instance, if we let x be 6. So when x is 6, then our y is going to be -6 plus 2 is -4. So it's a -4/3, right? So then this is like, you can check this one and it should work. 6 minus 3 times 4 over 3. 6 minus 4 is indeed 2. So that one checks out. 3 times 6 plus 9 times -4/3. Well, that's going to be what? 18 minus 12 is 6. And that checks out as well, right? You can repeat it for any value of x. You choose your favorite value of x, you find the corresponding y, and then that order pair should make both equations true. Yeah, negative, let me see, we said 2 minus x over 3, which is fine. 2 minus x over 3, okay? Okay, 10 more slides to go. All right, so again, one equation is a multiple of the other. Okay, so finding the break-even point and the profit function using substitution. Given the cost function and the revenue function, find the break-even point and the profit function. So the break-even is where the revenue equals the cost function. Again, that was our revenue function equal to our cost function. So then we want to solve this guy. Okay. If we subtract 0.85 from both sides, seven. Hey Google, what's 35,000 divided by 0.7?
35,000 divided by 7 is 5,000.
5,000, okay. So if we produce and sell 5,000 units, that's our break even. So then if we want to, anything over 5,000 is going to be a profit. So once we sell one more than that, then we start to turn a profit. All right. And then our profit function is going to take on the form. It's a revenue minus the cost. Okay. They got 50,000, 0.7. Maybe I didn't say something right. 35,000. Hey Google, what's 35,000 divided by 0.7?
35,000 divided by 7 is 5,000.
Oh, she thought I said 7. Okay. Hey Google, what's 35,000 divided by 0.7?
35,000 divided by 0.7 is 50,000.
Okay, that's fine. Yeah, we're good on the rest of it. Okay. So the cost of the ticket to the circus is $25 for children and $50 for adults. On a certain day, attendance at the circus is 2,000, and the total gate revenue is this. How many children and how many adults bought tickets? All right. Let's start off with a revenue function, money generated. Well, it says the cost of a ticket. Okay, for children and adults. Okay, so we're going to compare children versus adults, right? So the cost, let me see. I'm going to just say based on X and Y. Or I kind of want to say C and A, like for children and adults. Okay. Well, that's not our cost function. That's actually our revenue function, right? That's going to be the money generated. So the revenue, let me see. So it's $25 for each child plus $50 for each adult. So that's going to be our money generated. So the total revenue for that day is 70,000. Okay. And we had 2,000 people in attendance that day, right? So the number of children plus the number of adults equals 2,000. Okay. So we have two equations and two unknowns, so we can solve. I am going to multiply the second equation by negative 25 so that the c's cancel. Okay. So then if we account for this, the first equation stays as is. Let me see, the second equation now becomes negative 25c minus 25a equals a negative 50. 1, 2, 3. A number plus its opposite, these add to 0. So now we have what? 25a equals 20. Well, if 25 into 200 is what? 8? So 800 adults? Hey Google, what's 20,000 divided by 25?
20,000 divided by 25 is 800.
Okay. If we have 800 adults, then C plus 800 equals 2,000. So then C equals 1,200 children. So it looks like we had 800 adults and 1,200 children. And we should check this in the context of the original to make sure that it makes sense, but I'm just going to use my prepared notes. 800 adults and 1,200 children. Okay. All right, ladies and gentlemen. So that brings us to the last of the new material. If you are still with us, congratulations. Like, that is no small feat. So hopefully you've been making your way through this. You know how to reach me. Again, the best way to reach me for support is like just a text message or use my office cell phone number. We'll kind of be working and, I'll be available. And with that, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.